Good evening, everybody. It's Alex St. John, aka The Saint, streaming to you live from the Playcast Dungeon at what time is it here? Is it evening? It must be. It's not morning. It's 7:19 p.m. In sunny Redmond, Washington. Hope you guys are all having a great day. Who wants to help me out with something? There's all kinds of stuff going on, but first, I was just in meetings today where all the technology demo didn't go perfectly smoothly, so I got to figure it out. I'm up on twitch.tv on my company playcast.io Twitch channel, and I've got my server rack over here and I'm test streaming some games. And so we were, I won't say where because, business, but we were at a customer site and had terrible mobile reception. And the demo didn't go smoothly, which is really upsetting. It was low modem bandwidth, but even then, when people have poor connections, that's not an excuse for sucking. Actually, I got to figure out a way to make it work anyway. So I just wanted to verify that the server and all the stuff's working. So if you go, as I'll post this shortly, it's going to be live. And if you go up there, this is just raw testing, breaking stuff. So we host this stuff not as a, it's not a service up on Playcast.io. It's not content. It's us testing it. So go up there and break things, or have fun. Have fun and tell us if it works. If you have a sucky experience because of network or streaming issues, let me know. And if you, can want to kill the game and get on the server desktop and make a mess, do that because, the product has to be secure too. So everything's on the table here. It's Wild West. That's half the fun of innovating. So what you're looking at on our Twitch channel is not as this is Twitch TV. It looks like one person, the Tekken CPU is beating up a guy just standing there, and you see the QR code there. I got my phone here just in phone mode, and I'm just going to look over there at my screen and click, and I just picked up the QR code off the screen. I just scanned it on the monitor wall back there in the distance, and Tekken 1. So I'm going to click on Tekken. And I'm going to jump on that live Twitch stream here, hopefully, and see all the speed issues. Why is it taking time? We should be connecting. There we go. And that says, I don't know if you can see that, but there's Tekken in the background, and there's the Playcast icon. It says this game is giving me gamepad control. So I'm going to hit play, and you hear the audio coming through on my iPhone. There's nothing installed on this iPhone. The phone it's just a Safari browser. There's no app here. That's what we're trying. Now, I'm on the mobile network. I just connected to that game live on Twitch, and now I'm going to start it. So I'm just going to mouse down, and if you're watching the Twitch stream, it's 8 seconds behind on the Twitch stream. So because Twitch is not real time, I'm on a web page, I'm real time, but up there on Twitch, it'll follow through a few seconds behind. So I'm actually going to hit A to start the game. Select the character. I'm going to pick another character here. And again, you'll see Twitch catch up to this. But you see, I'm there. That's my experience. So it's behind. There we go. See the difference in latency? I'm having a real time. This is just a web page. And hit A to start a game. I definitely want easy for testing. A for easy. So I just clicked easy. And A to start. Oh, there we go. And now I'm starting the game. So you see the stream's behind, but I'm seeing a real-time stream. Okay? And then what level do we want to go to? I want to... looks like it's picking that one. There we go. So we're comparing the live Twitch latency to the real-time Playcast game stream. All right. Now I'm just on my phone in Safari playing Tekken. With my phone as the gamepad on a server over here in the barn over the mobile network. And if you want to see what that looks like, so I'm going to do a terrible job of, where's the button? There. See, I'm just kicking that guy in the face. Look how awesome I am when it's set in easy mode. So I am literally playing Tekken in the Safari browser. I think this is all working great. What we clearly need to do is optimize for those lower bandwidth or lower quality network conditions, because I'm just fine over mobile right here. So even though I'm sitting next to the server, that server is on the physical network. I'm on the mobile network, going out to, a telco to get it. So even though that computer's right nearby, it's not as though I'm playing on a network, playing on the local Wi-Fi network. All right, let me kick this guy again. Here we go. Let's see. Right, so I got Tekken up there on Playcast.io. I'm going to leave it running. Love to get some feedback. And again, I don't care what you do to it. Do anything you want to that machine. I'd prefer it if you played the game and said, hey, my latency, here's my computer, here's my connection. We're up in the Redmond, Washington area, that region of the world. So if you go have a great connection, the game plays fine. And tell me where you're at, your zip code, and how far away you are. Or if you have a bad experience, are you on a mobile network? What are you trying? Because I got teams of people all over the world who want to make sure this is a great experience for you. So that works pretty good. All right, so that wasn't bad. Okay, looks like we got a little optimizing to do, and I appreciate your help with that. But I'm actually here to talk about another subject. I just wanted to make sure that was working good. And actually, there's 8 different game servers up there with different games on them we're testing. You can play 4-player co-op with some of the games that are up there. Like I said, if you can break them, you don't find them all up and running. Well, that's the stuff we're testing. This is all in the world of software, R&D, and the consumer tech space. So since you are among my elite set of core gamers and possible game developers, I'll let you in on how the sausage gets made here, and take a look at the technology in development and play with it, and point you to the secret source, because we don't need everybody in the world beating on this thing. We just need a few smart people beating on it and telling us what works and what doesn't. All right, so I got a bunch of great questions from everybody that came up from my, now I shot my mouth off about the 50 series of new NVIDIA chips. I kind of have to go get them. Also, for those of you who are on my channel, I wanted you to know, tell you I have a subscriber base that really shot up recently from that video. Thank you, everybody. Smash that like button and subscribe. Got a few elite folks here that I'm going to out just a little bit. So just to know what vaunted company you're keeping, down there in my comments is Ken Nicholson. 30 years ago, Ken Nicholson was the ATI executive before ATI was acquired AMD, who was stationed at Microsoft. So ATI had their, ATI was, they were like a third-tier Windows chip maker. So their chips were really popular for DOS game developers, but they were also, they had they were a premium-grade Windows accelerator chip back then. And they, had somebody stationed on Redmond campus to, work with Microsoft, make sure the chips always represented well. And in that era, Cirrus and S3 graphic chip makers were kind of the dominant Windows chips. And when we started the DirectX project, we're kind of a skunkworks team of kids just doing our own thing without a real charter from Microsoft to go build it. And Ken did a very unusual thing. ATI was a significant company. Microsoft was a giant company. We were just crazy kids going, we're going to make games work no matter what. And Ken saw that and supported us from ATI. He said, I'll lend you ATI engineers. We have a license to Super Bubsy. I'll help you port that to early DirectX. I'll be the first one to sponsor your developer events. If you want to make this, we'll write the first DirectX drivers for you. And so even though ATI was kind of a third-tier chip maker, they weren't huge back then, we had no credibility, we had no budget, we had no resources at Microsoft, and Ken put the support of ATI behind us in that period, and produced the very first DirectX 1 SDKs with a lot of support from ATI. And the Great America Theme Park launch party in March of 1995 and the Great Judgment Day event were all sponsored by Ken. So the crazy marketing and launch events we did without any, with very little Microsoft support, were also very early supported by ATI. And so we're eternally grateful to Ken, and DirectX probably wouldn't exist without him kind of betting his career on it. And today, of course, as a consequence of Ken being in so early with the Microsoft gaming revolution, ATI chips are the graphic chips on absolutely all modern consoles. Everybody adopted. They have a 100% monopoly. So when you look back 30 years, I think if, I don't know if Ken still got options in AMD, but boy, that company ought to thank Ken Nicholson for 30 years of massive growth and success, because it was that one guy going, hey, I'm going to back these kids who don't have a charter to do this stuff. And it definitely really paid off for ATI/AMD today. So thanks for being a subscriber, Ken. Love to have you commenting in there. Some other interesting folks from the game industry in there. I won't out them all because I might value their privacy, but one of them was the legendary guy at Microsoft who trained the technology evangelists to kill Microsoft competitors. He wrote the book Evangelism is War, trained me and the original DirectX guys. The funny thing is we were trained to take over the market, to kill Microsoft competitors. But we turned inward on our own company with the sort of talents he taught us, and ended up, of course, taking over the Microsoft Media Machine to make DirectX. He ended up, all of his email and his book, Evangelism is War, Google that one, I think I've posted it in previous articles, are all in the Supreme Court, or all in the Microsoft DOJ antitrust documents to this day. So he was the evil mastermind that trained Microsoft engineer megalomaniacs to take over industries with technology. And without him, there'd probably be no DirectX, because we were all kids that he turned in. He looks like Santa Claus today, too. So really always feel this festive feeling around him. But James is here on the channel commenting periodically, if you can guess who he is. So another tech legend. And there's some others here, too, but I won't out them all. So welcome, and good to see you all here. So there were some great questions in the channel, and it made me realize, oh boy, I need to be a better communicator. Also, even though I just take kind of knowing all these things for granted because I'm immersed in the industry, I'm going, man, there are people got to be on YouTube, just got to be doing beautiful, graphic, animated videos of some of these topics, and there are. So I will go over some of the subjects verbally, and then I'll link those great videos that really go into it in detail, because I think they're so helpful and educational. And that's one of the things I love about YouTube, is hidden in all the crap is brilliant, long-form, very well-produced content that touches on all these things. So let's cover a few things. And I'm going to talk about core game tech. So if you're a game developer and you want to learn something, and the funny thing is, people go, oh, you're old and out of touch. Well, the weird thing that's happened in the game industry is that because the success of the old guys at making Unreal Engine and the Unity engine that contains and encapsulates huge bodies of gaming and media and simulation expertise, there's actually a whole generation of kids who grow up in the game industry never learning these things, because a lot of the magic to the illusion is inside the gaming platform engines that they use. And the reason these engines are so much easier to produce a game on quickly and cheaply is a lot of this hidden knowledge or expertise is built into them. So the weird thing is as with each subsequent generation, you often get more ignorance on the business and technology of gaming. Which again, you'd say is progress, because in some sense, this information is irrelevant because the market and technology has moved beyond needing this expertise to make a great game. But I think it's fun to talk about, and it's great science in any case, which we all love. And there are times when you have these debates about the technology when it's useful to surface this stuff. So I shot off my mouth. I saw a lot of questions. Thank you for all the comments. I love I got some smart other know-it-alls. I'm attracting another bunch of know-it-alls here, so know-it-alls are fun to quibble with. I love quibbling. They love quibbling. We're all happy here. So welcome aboard. Come on up here and no, it's not. Yes, it is. I'll be happy to participate in that. So those are fun. All right. But I got some great questions. So let me summarize some things real quickly for you. So first off, the difference between there's several huge differences that really matter between a console game experience and a PC game experience. And those differences, people, if you're just a gamer, you don't really necessarily think about them until you realize they're really quite profound. And I want to point them out so that and quantify them right here in summary form. So hopefully that a lot of the questions that I get up here as a consequence of my poor communication skills, I'd like to summarize them usefully for you. Okay, so the first. The way you experience video in a passive mode with your hands on your lap watching a big screen or a TV set is very different from the way you experience media interactively when you're clicking. Puts your brain and your physiology in a whole other mode. So one of the weird problems that creates in gaming is that when we are looking at streams of game content on Twitch, or when we are writing magazine reviews of a game while watching a game, our experience of the graphics quality and the game itself is almost entirely different. It's like in a whole other game than from when you're playing it. And so it's quite hard to consciously, deliberately view a game independently and be objective about it if you're not playing it, because the brain switches modes. And so one of the reasons that games put so much effort into fake graphics and animations and story sequences is those are meant to be viewed passively, and they're all usually meant to produce marketing videos and SEO content, search engine optimization content for the game for marketing purposes, and reviews. And the game content is often run and rendered very differently from those graphics. And consumers often go, that doesn't look the same, this is not video quality or render quality. And the truth is, when you switch to gaming mode, the video quality needs to be very different to be immersive. Often what you think is a lower quality or lower production value experience is also better for gameplay for a variety of reasons. And so this disparity consumers see between passive video gaming content or watching actual gameplay passively, which you do on Twitch, and actually experiencing it creates a lot of confusion in the market about how to whether the game is good or not based on those experiences. So I want to point out one big thing is when you're passively consuming video, your brain's in a very different state than when you are playing a game and you think you're being pursued by actual wolves and trying to save your life, and your brain is in fight or flight mode, which it's not when it's relaxing watching a movie. When your brain is in fight or flight mode, several amazing things happen. Time slows down. The more scared you are, or the more immersed in an intense game you are, the more your brain slows down time because it dedicates more and more resources. You have more thoughts per second, which equates to time slowing down. And your reflex speed increases because it's an emergency, so your ability to respond to input changes. And your visual acuity becomes more predictive, which means what you think you're seeing is more in the future than it actually is. And if you're a very practical computer science down-to-earth gamer, that's some crazy shit I just said. What? I've never heard that before. Nobody, no gamer moron writing magazine articles ever says this stuff because they don't know it. They don't know that's what happens. And so you get this kind of analysis, naive analysis by consumers of games that isn't informed by why the illusion works and what's actually going on when people are immersed in the game. So one, when you are playing an intense game, you are in fight or flight mode. Fight or flight mode is an emergency state your body enters to survive being attacked by something or a danger, an emergency. And games, good action games, put you in emergency mode. That slows you down the flow of time. That accelerates your nerve reaction time. That causes your brain to hallucinate or project further into the future. Because if you're being attacked by a wolf, it doesn't help for you to react after the wolf has torn your jugular out Your brain needs to be thinking about what to do in the future to prevent having your jugular torn out. And because you have one brain and one sense of reality, you don't know that your sense of time flow is your brain's projection of reality is actually set in the physical future from where your body is at. Because your brain's going, oh crap, I need to duck this wolf about to tear out my jugular. I'm going to go I'm going to put your consciousness in the future based on everything happening now so that you have a chance to react and deflect the wolf from tearing out your throat. That's what that reaction's for. And people aren't aware that that's what brains do when you're playing a game and it's intense. And so they confuse what their brain is doing, their imagination is doing, because of the state the game is putting their brain in, with what is actually going on their computer screen, what's actually being simulated by the game. And then they argue with me really vehemently or post clown pictures of me because you don't know what you're talking about, right? But again, and if you're a gamer and I'm spoiling your fun for you, don't watch this channel. This is for gaming professionals and scientists and people who are fascinated by deep, lengthy, intuitive discussions, not surface garbage, okay? So I apologize. Don't want to spoil your games for you. So if you feel like just being angry with me, just don't watch it. It's okay. You can click away, right? I'm sorry I'm so compelling, but the reality is that games put you in your brain and in a kind of in your body in an emergency state, and that emergency state includes interpolating more in the future. So I want to show you something fascinating because we were talking about the whole subject of DLSS4, which is this interpolated frame generation. And I wanted to, that's sort of a modern thing that came out where the games are generating frames in advance. And I kind of wanted to show you the computer science where this emerged from, because you see it all the time, and you have for decades, and nobody ever complained about it or noticed it, even though it was all around them. And out in the barn, things on the roof, trees everywhere, things falling on the roof. So I'm going to show you something fascinating, right? I hope it's fascinating, right? I'm just going to go to YouTube here, and let me give me 1 second. We find let me see here. We're looking for, let me think, what is the right keyword to find exactly what we're looking for? Oh, yes, optical flow is the word we're looking for. And, I don't want to be on YouTube. I want to get images for this. Optical flow. And weirdly, I'm an accidental expert on optical flow from years before I learned about it in video. Here's a good one. This looks like this was generated probably open in new tab. There we go. Okay, I will pull it up. There's my new tab. No, come on. Give me 1 second here. Open, and we went. Oh, right there. That's all right. Here we go. All right, look at this. These are such pretty pictures when you see them. All right, this is optical flow. Let's see if I can. An optical flow image looks like. All right. That can be a heat map. Actually, let me read it here. Long range running. I think that's a depth image. Sorry, that's the wrong. That's a cool looking. It looks like optical flow, but I don't think that's optical flow. There's another image here I'm looking at that is said to be actual optical flow, but it's not the best example of it, because when I do optical flow, I like to use the heat maps because I think those are so much cooler. Let me see if I can find a good example. And I'm just here, this will work. This will explain it for y'all. Let's see. Open in a new window. Let's try this one. Optical flow. Okay. Yeah. All right. Now, I'm going to zoom up on that so you can see this image. All right. Can you guys all see that? Just Google optical flow, and hopefully you'll actually get optical flow. Okay. All right. Let me just move my own face over here so you can see. All right. So what are we looking at here? So when you record video, like we're doing now, and stream it on Twitch or YouTube, well, we compress it. And how do we compress the video? Well, when you go to the movie theater, I won't over-explain this, but the way we compress the video is we take a look at all the bits in the image and think of a bit of video as just a sequence of photographs, right? And so what's the difference? Is a compressed video just a bunch of JPEG images of regular images? No, because if we did that, you would get all kinds of visual artifacts, temporal artifacts. Your eyes would see it would bother you in your compressed video. So we don't. So video compression isn't just a bunch of compressed JPEGs. We have to compress in the time domain as well as in the space domain. So video compression algorithms are three-dimensional. And one of the things they do is track optical flow. And optical flow is, for any given in a scene, any object here, let me make an object, let me find something. Oh, here we go. Okay, yep. Here. My flashlight. All right, so this object, if I assume I'm relatively static and I'm just going to sail by the screen here, well, most objects made of physical materials, right? As this object moves across the screen, its color space and its details don't change that much. So if I can do an optical flow analysis to detect that this group of pixels, this is a group of pixels in a video scene, because these pixels all move together, this set of colors all mostly maintain their color relationship as I move them in front of the camera, then this is something I can compress very efficiently. I can store it once and then just put slight modifications to it as it moves across the video and as the lighting changes on it subtly. So being able to detect a group of related pixels moving relative to the camera is really valuable for video compression. So we compute the optical flow in time to find groups of pixels that all seem to move together. Okay? And when you do that, you get something that looks sort of like, I like other ways of visualizing these things. But what you see here are optical flow vectors. So this is a car driving into a scene. So when you drive into a scene, of course, the environment parallaxes by you in a blur. So the trees and branches all have, the pixels are all on the edges seem to be moving at a high velocity past you. And so if I capture several frames of video, my brain, well, this is where I don't want to get too meta yet. We're going to stick to the computer stuff, and then I'll teach you the shit you never hear from anybody else. Okay? Here we go. All right. So as you're moving around in the world, we capture these optical flow vectors. So video compression algorithms, your codecs, they analyze a sequence of videos, they generate optical flow diagrams to detect groups of pixels moving together, and that's how you detect objects moving over time. And then those objects, because they are maintain about the same properties and don't change much, become much easier to compress efficiently. So really good video compressors detect optical flow. And all your hardware video encoders for almost 20 years automatically compute these optical flow maps for all video you feed them, and then use that information to generate these vectors. And what these vectors represent is they say, given the last frames, this pixel here is going to be at this position in 2 frames, at that position in 10 frames, and at that position in 100 frames. And then they compress the video assuming that information. Subsequent videos they check to see if the assumption was correct, and then they store little changes, just incremental changes where it's wrong, and where it's right, they don't even store the future data. So in other words, the way video compression works is the way your brain works when you're in fight or flight mode. And remember, I have said on this channel before that what people think, and this is one of my great frustrations with the 3D VR people, is our eyes are pretty planar. They're kind of on the same plane. The amount of depth we see is very shallow. Basically, 3D depth, as defined by two eyes viewing something from different angles, is really meant for being able to do this, right, without too much coordination. It's for our hands to pick things up. After that, the depth information that our relatively flat eyes generate, kind of useless for generating 3D depth. The human brain does not see 3D depth because we're flat-faced monkeys. We see 3D depth because our brains compute optical flow. We see depth in the environment because of the movement. And this was one of the major reasons that 3D television sets, which were this huge craze, and 3D movies were this huge craze, the industry tried to make that happen, kind of failed. And the reason it kind of failed is they were a bunch of brilliant engineers trying to make real 3D happen when the brain doesn't use real 3D to see depth. It uses parallaxing and optical flow to generate the illusion of depth. And depth, the 3D depth you see isn't real, it's rendered by the brain. And the brain is a future prediction machine because that's what it's for, is surviving being eaten by wolves. So if your version of reality, the thing you're thinking with, wasn't set in the future, it wouldn't be a very useful brain. Because what the brain's job is to do is accurately and instantly and instinctively predict future events so you can react to them now, right? Or that's not useful insight. I'm going to be eaten by a wolf in 3 seconds, duck, right? If I am being eaten by a wolf when it occurs to me to duck, natural selection has removed all those brains from existence because those aren't useful minds. That's not consciousness. And so in order to work, your brain doesn't have a deep metaphysical analysis about the fact that what you're experiencing is a future event. You just think you're living, your present is actually several moments in the future, especially in fight or flight mode. And your vision system uses optical flow to visually predict that future that you see and to visually generate the 3D depth you think you're seeing that isn't there. Okay? Now you're learning some shit. How about that? Okay? So, why is this fascinating? Well, remember, this is 20 years of video compression that's doing this. So you see these optical flow vectors saying here's where the pixel's going to be in the future? That's in every 3D piece of hardware since maybe even the 90s in a lot of cases, but mostly in the early 2000s. Well, that's kind of, and NVIDIA and AMD have been shipping that for their video encoders and decoders for years. You're seeing that every time you watch a movie for the last 20 years on your AMD or NVIDIA chip, you are seeing the movie encoded as optical flow vectors getting rendered into virtual frames, and everywhere the frame quality looked great but was compressed, it's because it wasn't an actual photograph of the future frame that you saw. It was the hardware and decoding chip following these optical flow vectors to predict those pixels and doing it so accurately you couldn't tell the difference between the compressed video and the fake video generated by the hardware decoder. Okay? Where am I going? So now it's the year 2025, and AMD and NVIDIA, the people who make these chips and have been making them for decades, and you've been enjoying video this entire time without ever thinking, wait, this is fake video. We just call it video compression. They start putting it into your GPU graphics. And again, I did a video, and it's apparently a popular one, with people going, oh, DLS4, I'm upset because you're faking the graphics, and it's not a real game input, and I hate it. And I have the temerity to bring you the bad news that all the video frames are fake. Because the game, that's the way the game works. Is the whole point of the illusion is to make you think you're in a alternative reality that your brain believes, where you're having a great effing time imagining that you're being chased by real wolves, and you're in fight or flight mode artificially to get you, because that's stimulating. You like it when you feel like you're surviving and overcoming threats to your survival. And so the game stimulates you to believe that. And all the computer graphics you're rendering, its entire job is to make your brain in that fight or flight mode and be consistent, to be good at getting your brain to be an accurate predictor of what's coming next. So let's start with a single player game as an example of what the game engine is doing. Single player games. So in the PC world, and it's different in the console world, but in the PC world, oh, hold on a second. Oh, gotta go, all right, it's almost bedtime. I'm gonna have to wrap this up. I'll pick it up later if I don't cover it all. All right, so in the PC gaming world, the computers are 10 years old, they're from different vendors, there's a whole spectrum of graphics, there's all kinds of different performance. And that makes it really hard for game developers to nail the frame rate, to nail the quality that they're trying to achieve on all these permutations of machines. So generally a PC game engine has 2 frame rates, really has 3 frame rates, okay? Let me see if this holds up. I might contradict myself in a minute if I remember 4 or 5 more while I'm talking, but let's start with 3. There are at least 3 frame rates, okay? There is the model frame rate, okay? The model is that inside the code is a loop that the game engine is going around to update its model of the game. Update all the graphics, update the AIs, update all the sounds, update all the inputs, incorporate them into the game. This is the single player game. So the model update rate inside the game is 1 frame rate that the game has. And magazines, game developer, gaming consumer mags, nobody ever talks about the model update rate because it's invisible, don't know what it is, and people who are game consumers don't understand that's how games work, okay? So there's a rate at which the world is being updated. There's a rate that time is passing in the game's model view, okay? And that's different from the frame rate, okay? So the model view updates at its own clock rate. Usually on a PC, it's a constant clock rate. So when I'm updating the model view on a PC, as I go around that loop, when I get to the next lap of the loop, I go, how much time passed since the last time I went around the loop? And it varies a ton. Might have been 50 microseconds, and then it jumped to 1,000 microseconds, and then it was 500 microseconds. But I go around that model view loop, and every time I hit it, I go, how much time has passed since the last time I made it around this loop, right? And I go, okay, well, so I need to update what is going to be seen on the screen between now and the next time I go around the loop, and I want it to be consistent. So if it took me, so let's say I'm trying to get my model view update at 60 frames a second, that's 17 milliseconds. So 17 milliseconds equals 60 hertz, or 60 FPS. 1760, 1760, okay? So if you say 30 milliseconds, right, really 34 milliseconds, that's, right, it's 30 frames a second. Okay, so the weird thing is, as the milliseconds go up, your frame rate drops. Which can be confusing, and I realize I interchangeably switch terminologies. So 17 milliseconds, 16.66667 milliseconds actually equals 60 hertz, or 60 FPS. Okay? So if I'm trying to update my model, that's not what you see on the screen, that's just where everything is in the game engine, and inputs incorporated, and sound mixed with the graphics and so forth, and the AI is reacting to whatever happened last. The time it takes me to go around the model, let's say it takes me, I'll make a dumb number, but let's say it takes me a millisecond to go around, then I go, oh, well, if I'm trying to hit 60 hertz, then the next render is coming in 17 minus the 1 millisecond it took me to go around. So I tell all my physics equations, calculations, and Mixer that the next time I go around the loop, the finished stuff that I'm working on needs to be from the future time in 16 milliseconds, because it took me 1 millisecond to go around the loop. If it took me 3 milliseconds to go around the loop, then the next loop needs to calculate where everything's going to be in 17 minus 3 milliseconds in the future, which is 14 milliseconds. Okay? So the model view is going around, and it's going around at different speeds, but always trying to update the model at a constant rate. by looking at the time it took to render the last part of the game state model and then update it. You with me so far? Okay, so the game has a model view. Then there's the frame rate. The frame rate is not the same as the model view rate most of the time. There are lots of different kinds of games written kinds of lots of ways, so I don't want to say always, but generally. So the frame rate of the game is the model view wants the game to always seem smooth and responsive, even though the computer's performance is usually varying unpredictably. Sometimes I'm running on an old flow machine, sometimes Windows is doing an F-thing update in the middle of the game, sometimes Discord's decided to page a bunch of crap in while your game is playing, and all that stuff is going on and fighting. So you get this huge variability in a PC game for how fast you go around the model view. So the game has to go, okay, I really gotta calculate when I'm going to update the model for the next frame. And in the meantime, because that's so unpredictable, I never want the user seeing all these fluctuations as I go around the loop. So I want a nice continuous frame rate. But hitting a continuous frame rate has the same problem. Nice thing is it's 3D graphics. 3D graphics are nothing but parametric equations. Nice, smooth, continuous equations most of the time. So if I know it's going to take me 3 to 7 milliseconds to go around the loop, my rendering loop can go, oh, I think I can we're running at, I think I can do 300 frames a second. And then I can do 200 frames a second. The next session I'll do 150 frames a second. But I'm just going to mathematically flood the display with generated frames. That's what the rendering loop does. They're all fake. They're all fake frames because they're all independent of the model. Okay? And those are just because 3D graphics are nice continuous mathematics most of the time. The GPU can just go, oh, I'll just keep generating fake frames until the next time the model updates. And so your video looks smooth and continuous and doesn't have a lot of artifacting because the GPU is doing that's what it's made to do. It's what it's always done is make fake frames while the model views are running separate at a different rate. Okay? And then these days the game is often projected or running against a physical monitor that has a constant refresh rate. Modern monitors actually support variable ones, which is cool. But in general, most monitors, unless you're a really core gamer and have the cool ones and have them all hooked up, the monitor refresh rate is traditionally running at a constant rate. 30 hertz, 60 hertz, 240 hertz, 380 hertz, 360 hertz, excuse me. And the problem is that if the game's rendering rate is different from the refresh rate, then it's like looking at a light bulb or a strobe light through a spinning fan. And so there's this flickering of harmonics where you have rendering graphics, very high resolution, very fine detail graphics, in front of a strobe light, which is essentially what the refreshing monitor is. And that can cause these weird harmonics that cause visual artifacts and eye strain. And when we get to high speeds, you may be seeing those, and you're getting eye strain, you don't know why. Because your brain picks them up and it stresses your brain, even though you can't consciously see it, it's happening so fast. So that harmonic desynchronization between the display and the game can cause these problems. And now again, it's really cool because NVIDIA, knowing that, said let's standardize G-Sync, and modern monitor makers are making monitors that refresh at the same rate as the game. And that can eliminate one of those problems. If your refresh rate is in perfect sync with the game, then you get rid of a bunch of those problems. And weirdly, the higher the resolutions you go and the higher the frequency of the refresh rate, the more types of visual illusions that bother your eye can occur from that strobing effect. So it's really important in game, even though it's an arcane physiological condition that naive game players don't really understand precisely. They think it's associated with latency, which is not true, really. I'll explain that. But synchronization causes the strobing and a lot of the eye strain and other types of artifacts. So modern monitor makers and chip makers are getting those things synchronized so you don't have that problem, which is really cool. So it may go away, which is exciting. Good, right? But you still have the problem of the game's refresh rate and rendering rate fluctuating. And even though it's not doing it against a strobe light, the weird pulsing of frames, of frame sampling rate in the game may still cause some types of eye strain or visual stress, even though it's happening at speeds you can't see. So I know less about that. That's a little harder to quantify because it's been a while since I tested all these things and really got into it. So I wonder, but I imagine it's a lot less. Okay. So the 3 frame rates. So one, it is always probably a better quality experience to make sure your refresh rate is synchronized with your monitor sync rate, even if that just means turning on vertical blank synchronization. Because once you get above at least 60 hertz, it's not really latency you're dealing with, especially in a multiplayer game, which nobody will want to hear. Nobody will want to believe you. Everybody will go, "You don't know what you're talking about, I know better," because they will never speak to anybody again who tells them the truth or knows it well enough to understand what the hell they're talking about. So remember I explained the model update rate and the refresh rate of the game being independent from one another? Well, what do you think happens with a multiplayer game? Okay, with a multiplayer network game like an MMO, a League of Legends, an Apex type game, the model rate's a lot slower. So the model rate for a game running a single player game can be a lot faster. I'm a little out of date here, but it might be running at 60 or 100 hertz independently of the refresh rate of the game, and it's really snappy and responsive. And so whatever responsiveness latency you think you're experiencing, is a lot higher quality in a single player game. But a network game has 2 models, or many models. It has the frame rate and the model view on your local machine, which is different from the online game community's model rate for the game. So to simplify, the model rate for a network game is maybe 20 frames a second. If it's a really low latency, if it's Fortnite, I mean, it's League of Legends. The latency matters. It might be 30 frames a second at best. It could be a lot lower than that. Because the reality is your network games, the speed of light, the fastest they can update a model is tens of milliseconds. Just is. No matter what, almost, right? And if you're playing an MMO over the public internet, it heads out into the hundreds of milliseconds. So the model rate of a network game is really high. It's really slow, incredibly slow, okay? And so the gamer's like, "No, my clicks matter, my reflex, I need my gamer mice for League of Legends, and I'm so skilled," and so forth. Well, that entire illusion that associated with esports, a big part of that's what's called the gambler's illusion, right? The reason gambling works, the reason Las Vegas is huge and nobody ever gets sick of gambling, the reason that people just sit in front of slot machines and pour money into them, pulling a lever, is because the games are designed to create the illusion that you can win, that there might be some skill, that you have an edge when you do not, right? And so the game gives you the illusion of very high control over your destiny and being very, one of the things slot machines famously did, maybe they still do, probably still do, right? You need 3 sevens to win this huge millions of dollars, right? So you put a quarter in, you pull the lever, and it goes ding, 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 ding. Strawberries, cherries, blocks, ding, 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 ding. 7. And then the next one, ding, 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 and then 7. And then it goes, ding, 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 7 cherries. Ding. Oh, so close. Oh my God, you almost got 3 sevens. It was so close. Now, the probability you're going to get 3 sevens was infinitesimally small, but they put on a big show of almost giving it to you. So you're just like, God, I'm so close. Let me just try it again. I'll just hit the button, and it goes, that third 7. No, never mind, right? So, multiplayer games, one of the things game developers learn the hard way, chess is a great game. It's a game of skill. And there's a reason why it's perfectly legal to gamble on games of skill. Because nobody wants to. So, not a threat to Las Vegas. The problem with gambling in a game of skill, the illusion you can win, is what happens in a chess tournament. If we said we're going to start not the League of Legends tournament, we want to start a $20 billion chess craze, just have tournaments of teenagers just battling over chess, pure intellect to intellect, no randomness, nothing but 100% chess skill. Well, 1% of people would win all of the contests and everybody else would never win anything. And then all the people who lose would stop paying, stop attending, and lose interest in chess. And that's what happens. So if the game is actually a game of skill, if that latency in your responsiveness and how precise your moves really dominated your chances of winning, it would exclude most of the players. So we all learned that a successful esports game designers all learned that a successful esports game, a successful game that just lasts for years and milks money out of you like cows and makes you watch Twitch riveted to some esports celebrity showing you all the moves for hours and hours at a time, year after year, milking billions of revenue out of the market. That's a game that's got to make everybody feel like they can win, they're constantly making progress toward getting better, and that the game really requires, with enough practice, with enough determination, you too can have the skill to be one of the champions. Right? And so a whole lot of physiological and gambling instinct demand goes into designing those games to make you feel that way about them when the game is 50 to 100 milliseconds latency. Sorry, that's the reality. And it's an illusion that your click and all your practice and all your tactics and all those things are real, just like that 7 that just goes, you're almost brilliant. You can almost be a diamond level. You're almost there. Just keep practicing. You're almost a lucky winner of Megabucks. And that's how those games are designed to make you feel. It takes an enormous amount of research, experience with game design and time to refine those games to be so freaking good at it, right? And they are. So a game like League of Legends is highly designed to hide from you that its model update speed is incredibly slow. Because networks are incredibly slow. And the way that works, remember I told you the frame rates, that's independent. So when you're playing League of Legends and you go, and now, bam! Oh my god, my field is lightning, I'm flash. I hit that button in half a microsecond, that's how fast I was. And my 300 hertz screen and my NVIDIA 5090 GPU went bam, and I saw it on the screen as soon as I hit the button on my 1600 dpi mouse. But you were in fight or flight mode 0.3 of a second in the future. And you imagine that. And it's not what actually happened. What actually happened is you saw something on the screen. You go, oh, he's going for that thing. I'm gonna blast him before he gets there. But the person you're seeing who's moving on that game, that happened 100 milliseconds ago. They saw it on their screen 100 milliseconds in the past. It's another time zone by the time it drifted slowly over the internet to your frickin' computer. And when you snapped out that response, you saw something happen on your screen instantly. Boom! I got him! And the message that happened is drifting slowly and gently over the fabric of the information superhighway, bouncing off cloud routers. It's getting encrypted, decrypted, protocol corrected, gently wafting out to everybody's machines, and then they see the effect of that. That's what really happens, okay? And the reason the illusion works is because the multiplayer game engine itself does temporal warping, does relativistic calculations. The spells, the cone of the weapon fire, the cone of the spell impact, the wind down times of every spell are designed so that when you cast the spell, you see an instant visual response that seems incredibly low latency and meaningful, when in fact the cone of influence, the time frame of influence, were so effing fuzzy that it all actually was resolved in 100 milliseconds. And it didn't matter. You could have clicked that spell anytime. You could have used a 1990s Microsoft trackball mouse and clicked, 20 milliseconds later and achieved the same result. Right? And so a great esports game has a combination of economics. It has a mix of real skill, there has to be an element of skill, and luck. And those two have to be so closely balanced that humans' natural sense of delusion causes them to think that they're better than they are and faster than they are and are this much closer to improving their chances of winning than they really are. Okay? So the model view of a network game, the ones everywhere, first person Fortnite, I'm blazing fast. You go, oh, sure, single player, casual. If you're playing Bejeweled, sure, you don't need a fast gamer machine or GPU for that. But I need a 300 megahertz display and a 5090 for me to be competitive at an FPS. That's an even effing slower game, is what that is. Don't want to ruin it for you. This is why I waded deep. I just said a lot of other words to lose everybody who's a gamer. So game designers here, the people who are in the industry or just intellectually interested, but the snappy, fastest, low latency games you think you're playing, it's all an illusion. And because you're running that giant bloated client you had to download, it's responsible for that illusion. Because it takes all that expensive hardware and mouse to give you a really instant feedback on the screen that did not matter to the game. It's just, you look at it and go, damn, I'm fast. I got that guy. I'm so good. And actually what you were playing was a slow, ponderous game of checkers. And within the time frame, the move might have been strategic and beneficial, but it happened in the past, or you were in the future when you made the move. So inside a multiplayer, especially a large-scale MMO, is relativistic time, where your reality, other players are, whatever they're seeing happened in the past relative to your point of view, and whatever you do is the future relative to their point of view. And that's why those games are so addictive and seem so low latency and responsive when they're the slowest effing games anybody's playing. They're the most sluggish games, latency games you can play. That because of that illusion, because the graphics respond instantly to your immediate click, when the actual world update is taking a long ass time to propagate through that network. And so the games, I can look at modern multiplayer games and I can say, let me point out all the things they've done here to hide all this latency from you in the game design. And to keep you button mashing intensely, so you feel like the harder I run, the faster I'm getting away from that wolf chasing me, when in fact you're running in place. and they slow down the wolf just in proportion to how hard you think you're running, so that everything feels right. So that's what's going on, whether you like hearing it or not. So post those clown newses if you don't like hearing it. If you're a teenager and I'm ruining Christmas for you, I'm sorry. That's how it works. And what do I know about it, except that I made all that shit for you that you enjoy. All right, so now, there were some other numbers that came up in the questions. Let me look at the community page here real quickly. And so people were asking me about numbers. Oh, this was the thing about video. And so why? Remember I told you movies and TV shows really essentially filmed at 24 frames a second, or meant for 24 frames a second. So here's where this all comes from. This is where the world got weird, and I'd love to say I have a quick answer for this, but I actually need to catch up on a few things. So what happened is, remember when you sit in a movie theater with your hands in your lap and watching a movie, that's a relaxed condition. Now, to be a good action movie or horror movie can put you in flight or fight mode, which is why a jump scare movie gets you jumping in your seat. And so there is a blurry line here. But remember a movie is always meant to be seen on what? A silver screen. It's called a silver screen, right? Does a silver screen have pixels? Is a silver screen meant to show nice text so you can word process on it? Or is it trying to show you this magical world that you just feel like it's just an extension of reality, right? So in order to make a movie seem like an extension of reality from the theater's point of view, that screen that you see a movie on has no pixels. And the giant laser projector up in the control room is not drawing pixels on that screen, it's drawing continuous lines of video. And it's not, the laser isn't flashing on and off, it's generally gradually changing colors as it scans the screen. So that even if the movie is made out of pixels, what you're seeing is continuous color, okay, on a screen. And that's used to be how TVs worked, is you just had phosphors covering your screen and an electron beam scanning the screen back and forth, lighting up those phosphors with the beam going on and off. And when the beam hit a phosphor, the phosphor would light up and glow for a moment and fade away. And while it was glowing for a moment, the beam might have finished drawing the page, scanned to the top, come back down. The phosphor that it hit a moment ago is still fading, hit it again, glow. So the phosphor would never turn black, and then on, and then black, and then on. And the phosphorus had no mask of black substrate separating it into pixels, so that there was everything was a dot. Each phosphor was a dot with a black edge around it, because that's what you needed to see text on a computer monitor, but not in the movie. So the movie screen, silver screen, was a fuzzy, pixelless surface where all the color is continuous, and so was your TV set when the movie came to TV for a different physical reason, right? And now we all love our LCD screens. We all love our LED screen, not LCD. Look at my plasma screen. We all like our LED screens. Well, those LEDs, they're tiny laser diodes. Light comes out in one direction. So if anything ever formed a perfectly round, direct pixel at your eyes, let's say, separated by little solid black mass to make them absolutely perfect for rendering nice, sharp, crisp text that you can see. And those lights, they can turn off and on in fractions of a second. Then on, off, other way around. On, off, right? And so the effect of playing an old school, even today's modern movies, on a screen like that is this cacophony of tiny laser beams flashing on and off at your eyes, lighting them up with color. You go, well, what's the difference? What's changed? Well, those movies were not designed to be displayed that way. They're not meant for it. They don't look good that way. And they may have visual artifacts that you didn't see on the silver screen that emerge when you play them on a computer screen because of that. So you have to run the frickin' movie at a higher frame rate and render it at a higher frame rate on a screen with those physical properties to create a better illusion of the nice continuous tone that looked good, right? And that's exactly what your games do, is your games are like movies that aren't authored at 24 frames. The model view of the movie, of the game, is 24 frames a second, might be 24 frames a second. But if you've got a 300 hertz monitor with a 5090 GPU, then the movie is continuously rendering all the graphics in between that make the video look nice and smooth. And you go, well, that's better. That's why I bought the low resolution laser diode screen and the higher GPU. Yeah, but you didn't need it. You needed it because you bought the higher resolution screen, which was pounding your eyes with flashing colors, triggering epilepsy in some people. And the only cure for that, once you accepted, once you bought it, was to do it even faster until it was so fast your brain couldn't register, and it was just as sharp and high quality as watching it on a blurry screen was back in the days before your monitor was that high res and could flash that fast. So it's a brilliant act of marketing to sell everybody that they needed this heavier computer and display to render better, when actually those things were part of the problem in the first place, reducing the quality because of the way the media is produced. So I need a faster GPU to render more intermediate frames, because all that flashing with laser beams somehow hurts my eyes. It's not smooth, right? So it's funny seeing that. And again, I'd love to catch up because the physiology has changed. But let's get, so back to some other details. So I put the reaction test on the website. I linked it, a little 6-minute video I made today. Just go try it. Try it, but it's upsetting because you'll say it's all it is a game where you see a red frame and the second you can tell it turns green, click. That's all you have to do. That's all you have to do. Try to click faster than 250 milliseconds. That's 4 frames a second. Try it. Try to click 10 frames a second. Try it. Use any gamer mouse you like. Use your fastest screen. Use your biggest GPU. You will never freaking click. Unless you get lucky, 75 milliseconds. You won't, right? Because your brain can't do it. But you're not aware that your brain can't do it when you're playing a fight or flight risk because your brain is in the future. And so your brain is in the future, it renders a future where your response time is faster than it is. And you think you've got cat-like reflexes because your brain, you're playing a game that's an illusion that's put your body in fight or flight mode. So you think you're the Flash when you're in that mode. When you're in bullet cam mode. That's what's so cool about bullet cam, right? That's what the game does, and your brain really does that, really puts the world in bullet cam mode. So you think you're faster, you have more cat-like reflexes. The slowest effing games you play, you think are the fastest ones. They have the slowest model update games or the network games, and you think, oh, that's League of Legends, I'm so skilled. I need so much hardware to have an edge at this, right? And of course, and again, League of Legends is a skill game. We all know that there's people who are better at it, more consistent winning than people who aren't. But you know, it's where you mix a lot of strategy and other things in addition to reflex time, because it really isn't a reflex time game. Okay, so eye response time, the fastest you can see something, 5 to 50 milliseconds. That's 5 milliseconds, right? 17 milliseconds, 60 frames a second, 5 milliseconds, right? That's about 160 something frames a second. Fastest you can go 50 milliseconds, more for most light, 50 milliseconds, right? What is that, 20 frames a second? That's how fast you can see. The speed with which your brain can recognize something and send an electrical signal to your finger to click is so freaking slow, 200 milliseconds. So your reflex rate under ideal circumstances when you go, oh, a wolf's going to grab my throat, grab me by the throat, kill me, I need to duck, 1/4 of a second. You can move at 4 frames a second. Typically. With a lot of exceptions, there's some dynamic range to that, but nowhere near 160 or 300. Nowhere near the tiny 1600 DPI resolution Mickeys that your mouse supports. That's an illusion, and it's a good one, which is why reality seems like such an awesome place to live in, even though our body is actually pretty slow sensory organs, constructs a really nice, pretty picture of reality for us. All right, so that's good. I hope I answered your questions. So fastest that you can see something, 5 to 50 milliseconds. Fastest you can react to it, 200, 250 milliseconds. That is drive a click on purpose. I linked in my previously human reaction time webpage. Don't go wasting my time posting nonsense clown comments on my page. Go try it. And if you're such a smart guy, show me the video of you beating it. Show me your 20 millisecond click time, response time. Go ahead, just do it, okay? Otherwise, you know, don't let me spoil your day just because I'm explaining how your games work. All right, so I wanted to show you the optical flow stuff because I thought that was really cool. So, and this is the point I was going to make. And weirdly, in the AI world, right? So, for 20 years, video codec's been predicting the future. That's how they compress things. And then they interpolate the thing in the future for it to be compressed. By the way, that's how ChatGPT handles text generation. It's also a type of compression algorithm that predicts what's going to follow from the sequence of words you gave it naturally. And it just has such a huge database that's bigger than your dumb monkey brain. And so you're fooled into thinking you're talking to it because the database is just bigger than your human memory can handle. It can handle more prediction than your brain can handle. And so you think it's thinking, when actually it's just effectively decompressing, things that are predicting much further ahead than we ever had the computing power to predict ahead before. So, video compression uses optical flow to predict the future. The human brain uses optical flow, or more like optical flow, to predict the future and put you in a reality that's in the future in order for your survival to work in fight or flight mode, which is what a good game is meant to inspire. Which seems much faster to you, your ability to react to it, because it slows the world down and you feel like you got a faster response time. But physiologically, if you just run the test, you'll see you're not that fast. Finally, I want one mea culpa. Oh, and not a surprise that the GPUs that were designed to fool the brain's model of reality by simulating it also are the AI chips, because they're doing the same thing effectively. The thing the OpenAI guys are doing with text is the optical flow version of text. All right, the optical flow version of compression. So this is video compression that uses optical flow to predict the future. And the better you are at predicting the future based on optical flow, the better your compression is. And the better you are at predicting what comes next in the sentence. The quick brown fox jumped over the further you can predict the future. Because if the quick brown fox jumped over the lazy dog, the more words you predict in the future, the more prescient you are. And so if you build a model that predicts further into the future based on more and more past context, pretty soon your giant data center, backed by all the electricity combined of the Hoover Dam, is storing so big a model that the little human monkey brains can't tell the difference between a database lookup and talking to a thinking computer that out-reasons them. It's a really powerful illusion. Same chip, same idea, same type of illusion. So I hope you learned something if you stuck around this long. I'm Alex St. John, aka The Saint. I'll see you next time. Smash the like button and subscribe. And if you have more good questions for you, if I baffled you or contradicted you myself again, let me know and I'll be happy to address it. By the way, I don't mind contradicting myself. I see things from a lot of points of view at the same time. And I find sometimes when I'm doing these presentations, I don't sit around teaching classes all the time, teaching people. I just turn on the camera and freeform it. And sometimes I'm learning as I go. I went, as I think about it, this thing I thought a second ago, I actually changed my mind about. Like somebody said, wait a minute, don't you also need a lot of GPU memory to store the model in? I go, right, of course you do. Duh, what was I thinking? Sorry. So anyway, I appreciate the viewership and I appreciate the jump in subscribers. Enjoy your games in spite of me, kids, and I'll see you next time. Take care.